Okay, good morning everyone. So first I want to say something again about the residue theorem, because last time it was a little bit confused. And I apologize for that. So I want to start today. Maybe I'm the first person writing on this blackboard. Yeah. Okay, new blackboard, welcome. Okay, so residue theorem. Let's say that this is the general form. This is my abbreviation for general. Okay, so the general form. So what I want to say is that basically it holds also for essential singularities. Okay, so the theorem is the following. So FC is analytic. So it's meromorphic. So analytic except at isolated, except for isolated singularities AJ in a region omega, then we have the following formula that you recognize. The integral along gamma of f of z dz is equal to the sum of over j of n of gamma aj, so this winding number, times the residue at z equals aj of f of z. And this is true for any closed curve, gamma, homologous to 0. Okay, remember this, homologous to 0. Such that it doesn't pass through any of the isolated singularities of the function. Okay, such that none of the aj are on gamma, so none of them are in the image of the curve gamma. Okay, so this is the general form. So in particular, essential singularities are allowed. Okay? So this is the point. Now, you might wonder, how do we make sense of this right-hand side? So last time I said, we were discussing this fact, does this have to be a finite number of singularities or not? Okay. So this is a sort of hypothesis that you put if you want to explain it with less subtleties. But you can still do this. You want to make sure that this is a sum that makes sense, something that converges, okay? But it does. So the remark is the following. So the remark, to make sense of this right-hand side, we note that in fact there can only be a finite number of points aj where this is non-zero. Okay? And how do we see this? So, to make sense of the right-hand side, RHS, the right-hand side of this equation. So to make sense of this, let's see if I can do that. Divide it into 3 now. The blackboard is bigger. So note the following. Note that the set of all the points in C such that n of gamma of a equals 0, so all the points where the winding number is 0, okay. Note that this is an open set. Okay. Sorry? Who asked the question? Yes. No. Equal to 0 is open. Okay, so just intuitively, so I understand that you don't like something equal to 0 to be open. Okay. But, so take some curve here, and you take the winding number. So winding number is 0 outside of this curve. Okay. So this curve is a closed set. Outside of this curve, here it is 0. It's also 0 in a small disk here because you're still outside of the curve. Okay. So you can actually see this is open. So if you want to write something down and not just to draw a picture and understand it intuitively, just remember that we showed that this was constant on connected components. Okay? So constant on connected components. And I'm talking about the connected components defined by the curve gamma, meaning now we have the inside and the outside, but you could have several insides in several chambers. Defined by gamma. Okay? And gamma is a closed set. So you can see that this will be open. Now, how do you use this? Moreover, n of gamma of A equals 0 on the complement of some disk, okay, for R large enough. Okay, so this is clear. So outside of the circle big enough, you're simply outside of gamma. If I take the circle large enough, outside of the circle is 0. Okay. Now, so this you were asked to prove this, I think, actually in the homework. Right? Yeah, I think you were asked to prove this in the homework. Something like that. That on the unbounded connected component, the winding number was always 0. You were asked to prove this. Okay, so what is the conclusion? So all of this implies that the set of AJ, okay, you see, such that n of gamma AJ is not 0. Okay, so this is now a closed set inside a compact. Okay, so inside K compact, and it is closed. Sorry? Well, okay. What was the problem? Oh wait, there is a problem first. Yes.
Is that the complement of the first set? Because also could be that the winding number is not defined.
Yeah, but so I'm saying that it's inside the complement of this this set, which is I understand what you're saying. But what I'm saying is that if you look at all the AJ, such that this is not 0, then it has to be inside some compact set. Okay, and these AJ are isolated singularities. So this is some discrete. This is some. So yeah, and then so the last line here, hopefully it will clarify things, is that these points are discrete and they are inside some compact set. Okay, so I'm not saying saying it's inside some compact. This is discrete, and what does that mean? It means that there are finitely many of them. Okay, discrete set inside a compact. So whatever your notation for cardinality of this thing, but let me write like that. This is compact. Okay, it's not really end of a proof, but end of your remark. Okay, so it means that there are finitely many AJs such that this is non-zero. Yeah. Such that n of gamma AJ non-zero is finite. So this means that when we take this sum, then we have a finite number of non-zero terms. And so we're good. There is nothing problematic going on. We don't have to worry about convergence of this thing. Okay? So this is the remark. So in particular, as a consequence of this more general formulation of the theorem, the residue theorem applies also to essential singularities. Okay. For instance, if we take f of z, let's take our canonical example, e to the 1 over z. Okay? So, in this case, let's just try to do a very simple example. So, of course, we know this is 1 plus 1 over z plus 1 over z squared plus times 1 over 2 factorial, and so on. Okay, and the residue of this is therefore equal to 1. So, coefficient of this. So, residue. So, okay, of course, this function has an essential singularity. So it only has one singularity, right? Essential singularity is z equals 0. And the residue at this point is equal to 1. And one remark here is that when we have essential singularities, we don't have usually these brilliant formulas that we can use, because we always have an infinite number of terms in the singular part of the Laurent series, so we cannot get this coefficient of 1 over z by differentiating n times or such things, okay? So we have to rely on looking at the power series or the Laurent series expansion. So if I ask you to, if you have maybe some integral where you want to apply the residue theorem, and there is some function with essential singularities and you have to compute the residue, then you should manipulate the series in general. So if I ask you the residue of e to the 1 over z times z squared, then it's easy. You write down this and you multiply it by z squared, and you find the residue. Or if I take sine z times e to the 1 over z, you can write down the power series expansions of both, you multiply and you see what coefficient you get. Okay? So this is how you do it. And now as a consequence, so by the residue theorem, this means that if I take the integral of e to the 1 over z dz along, let's say, the unit circle, which now winds around once around the singularity, which is at 0, okay? Unit circle goes around once. Now this is equal to 2 pi I, so to get this factor, times 1. Okay? So this is equal to 2 pi I. This is the way you can see it. Okay, so this was a simple example. And finally, okay, I want to just remark that the proof I gave last time still works. Still works if you're a little bit careful with justifying this convergence of the now infinite number of terms in the singular part. Okay. And what I said that we do, so in the proof we assumed that we had only one singularity, right? So we had this picture. And then I said that if you have several singularities inside some gamma, you can always do the usual trick. Okay, you have A1, A2, A3. Then you can always take some curve here, C1, C2, C3. Okay? And so this one goes around counterclockwise, and this one goes around. So then you can look at, you can make a slit here where you go back and forth along the same lines. Okay? So this usual trick that I've always sketched. So I don't know if this is clear to you or not. Tell me please if it's not clear what I'm doing. So then you can look at this curve, C, which is equal to or C tilde. So C, let's say C is this outer curve that we're actually interested in. So then you can look instead at C tilde, which is C minus C1. So C1 would be always counterclockwise, okay? But if I go in here, I will go the other direction. So it will be minus this direction, and then minus this direction, and then minus this direction. And here I go in and back along the same thing, so they will cancel out. So this is equal to C minus C1 minus C2 minus C3. Okay, and then the integrals, so this means that the integrals along each, so it's additive, of course. So it means that the integral along C will be equal to the integral along C1 plus integral along C2 plus integral along C3. And if you show that each of these is equal to 2 pi I times the residue in here, that's the winding number. So the winding number here is 1, just like the alpha 1. Okay? Then you just sum them and you get the general form of the theorem. Okay. So that's all the remarks I wanted to do, or certain corrections I wanted to do on the residue theorem right now. And now there is the question, what I go to. Now I have two choices. Either I can continue with some examples of the residue theorem, or computational examples, or I can give a more theoretical application first. And I told myself I will decide on the spot what to do, because both work. I mean, last time I left you with the Jordan lemma, right? That you had to prove. But I think I will go to the more theoretical application first, assuming you're up for that. So let me talk about, because you've all seen how to compute residues using the residue theorem. We will do it, okay? We will give you these examples. We will give you the log and all these things. Actually, there are 5 types of integrals that you can compute using the residue theorem. There is a well-defined classification of sorts where you can use a certain technique in each. So you remember we have this course book that we use, which is Alfors. I don't know if did anyone look at this book? Okay. The book of Alfors? So, in there, I think or somewhere around page 159 or something like that, they consider all the classes of residue integrals. And so you can really, if you can really learn. It's a few pages long, but around page 159 maybe, from memory. But you can really learn these 5 types and see what to do. And there is no magic to it, right? But I will go through some of them for practice. But first, let's look at the argument principle, which is a fascinating application of the residue theorem. So the argument principle and other consequences of the residue theorem. Okay, so let's consider this. And the question now is, how many zeros and poles does a given meromorphic function have inside a given contour C? So the question. How many zeros and poles does f, a meromorphic function, have inside a given contour C? So we consider a contour C or gamma, and now we wonder how many zeros does it have inside. So these are perhaps the zeros. And then you perhaps have some poles. They are maybe here. Okay, how many of them are inside this curve and how many are outside? So of course this question is most useful if you want to determine where the zeros and poles are. Because not every meromorphic function is of the form 1 over z squared plus 1, where you can just say the poles are in plus minus I. So it could be hard to determine where the poles are and where the zeros are. And you might not know. In fact, as I told you in the first lecture, the most famous unsolved problem in all of mathematics is the Riemann hypothesis, which deals with an analytic function, and you wonder about the zeros. So you want to show that, Riemann hypothesis is that all of the zeros are on this line, real part of z equal to 1/2. Okay? So all of the zeros are on this line. Nobody knows, but if it is true, everybody essentially believes it must be true. And why do we believe it must be true? Well, actually the argument principle has helped a lot. Because you can use a computer to decide, okay, I will write down the theorem here. So it will say that the number of zeros can be counted by computing a certain integral, okay? And the computer can compute this around so you can take a rectangle here, for example. How many zeros are inside this rectangle? Well, you can use the argument principle in the computer to compute this number. Okay, it will be an approximation. It will give you maybe 6.97 because computers compute like that. But we know that the number must be an integer, so then we are more or less sure it has to be 7 if the computer gives you 697, okay? And then you can do this for any rectangle. You can do it over here, no zeros, okay, you do it here, it has this many zeros. You can do it everywhere. And you seem to verify this way that it seems very likely that all the zeros are here. We cannot find any other zeros. But of course it's not a proof. So the most famous unsolved problem in mathematics is finding a proof. But this is a good way of testing if at least it seems plausible, this Riemann hypothesis. Okay, so that is a remark. So what is this thing? How do you do it? So the magic is that this is related to the following integral, to the integral of f prime of z over f of z dz. Okay, and to get an integer, we divide this 1 over 2 pi I. So actually this would be, so if you have a curve that winds around once, like this one, so if I had a function f of z defined in the neighborhood here of this curve, then the number of zeros minus the number of poles of this meromorphic function would be equal to this, which is kind of new. And you see this is what the computer then computes. Because you can compute integrals numerically along any such path. Okay? Of course, you can sometimes compute it by hand, maybe, but not if it's a difficult case. Okay, so, and of course, okay, so it counts the number of zeros minus the number of poles, but if you have an analytic function, then you know you only can only have zeros, so then it counts the number of zeros. Okay. So, now, more precisely, what is the theorem? And it is called the argument principle. Okay? So the theorem says the following. So take f meromorphic on some omega with zeros aj and poles bk. So of course there could be a priori a different number of zeros and poles. So these are indexed by j, these are indexed by k. Then you have this integral, so 1 over 2 pi I, integral of gamma of f prime of z over f of z dz is equal to the sum of the winding number around the aj's, okay, minus the sum of k of the winding number around the bk's. Okay, so, and this is true for any, as usual. So it's not a surprise that these hypotheses are always the same. For any closed curve, gamma homologous to 0, such that neither of the zeros or the poles are on gamma. So these hypotheses are always the same because they essentially all rely on the same tower or logical chain of theorems that we are proving. So now, why do I say, so this is equal to the sum of the winding number around the zeros minus the sum of the winding numbers around the poles. Now why did I say that it counts the number of zeros and number of poles? They count the winding numbers. Okay? So, of course, this is a slightly more general statement than what I said, but the remark is if these two quantities are equal to 0 or 1, okay, always. So we take a curve that winds around each 0 pole at most once, okay? Then we should see that this thing here, let's call it star, then star is equal to the number of zeros inside gamma minus the number of poles inside gamma. Because then, whenever this AJ is inside, this is equal to 1. So if it was inside, we add 1. If it is not inside, then this will be 0, so we will not add anything. And in the same way, if a pole is inside, then we add minus 1. There will be the number of zeros inside gamma minus the number of poles inside gamma. Okay, very fascinating. Now let's see if we can understand why this is true. So let's do a proof. Okay. So first we get, so what is magical about this f prime over f business? Something is clearly going on when you look at this kind of quotient. And what is going on? So let's just see here. So if f has a 0 of order h at a, then what does that mean? It means that we can write, so this is extremely important. This is the fundamental technique in complex analysis. If you don't know this, you cannot do much. So what is the trick? I want to write it as z minus a or h
times something which is not the
yes. This line is one that you will use many, many times. Okay. The exercise sheet of the exam where you never use this line does not exist. Okay, so this is a good line to know. So you have this. And now if I look at f prime of z, okay, so let's compute this. So it's equal to h, z minus a, h minus 1, g of z, plus z minus a to h, g of z. G prime of z. Thank you. G prime of z. And so f prime of z over f of z is equal to now h over z minus a, this is the first term, okay, plus g prime of z over g of z. Right? Now, this one here is holomorphic, and it's not 0. Yeah, it's holomorphic because g of a is not 0. Okay. So this one here is holomorphic. I write it in another color. So this one holomorphic. Nowadays, I tend to switch to the word analytic. So let me stick. So analytic as g of a is not 0. So I divide by something, and you know that this quotient is analytic, unless what you divide by is 0. This neighborhood. So this is not 0 in A, so it's analytic in a neighborhood of A. Okay, and this means what? This means that this one has a power series expansion with only positive terms. I mean, in Laurent series expansion, the singular part is 0. So the singular part of the sum, this will contribute nothing. Which means that the singular part will be this, and the residue in z equals a of this f of z, no, of f prime of z over f of z is equal to h.
Find the one dimension.
That's what?
No, okay.
Yeah, it's equal to h, which is equal to the order of the 0 of f of z. Okay. When I write this order of z equals a of f of z, this is a number. I mean, that would be this means the order of the zero.
No, I mean to integrate the two parts.
Mm-hmm.
It becomes h times the winding number of gamma.
That is very true, and this is what we will do. Okay, so in the same way, so if f, we just have to check what happens when we have a pole. Okay, so if f has a pole of order k at a, then what do we have? F of z, this is the other line you will always use. What do we have now? Exactly. G of z over z minus a to k. The g is analytic, and g of a is not equal to 0. So now we do exactly the same thing. We see that f prime of z over f of z is equal to minus k over z minus a plus v prime of z over g of z. Okay, so this is what we will see. Because now we divided by k, so when we derive, we will have the minus k coming out in front. Okay, so we get this. In the same way, this is analytic around here because g of a was not 0. So hence the residue here, z equals, okay, maybe I wanted to call it b for psychological reasons. But now if a is a pole, then the residue is equal to minus k. Okay? Well, actually I want to call it b. Let me call it b. I'm sorry. It's not so many places to change. Z minus b. Okay. Psychologically now we have zeros in a's and poles in b. So the residue is minus k. Now, we do exactly what was suggested here. We're calling so by the residue theorem. Now, so to make it clear that this is a corollary of the residue theorem, we have 1 over 2 pi I of this integral along gamma. So gamma is any curve that we allow according to the hypothesis I put on the board, right? Any such closed curve. So the integral here is equal to 1 over 2 pi I times okay, so it's equal to 1 over 2 pi I, and then you have it's equal to so it's equal to sum of winding number times residue of f minus the sum of k of bk Okay, now this is the residue theorem. This is what the residue theorem says, right? I've only copied the residue theorem. So, I mean, of course, I understand your point. You want to see how this winding number appears.
Is it plus?
Plus, thank you. And the minus will come from here later, yeah. So this is equal to sum of gamma aj, because this times the order here. Okay, because the order, the residue was equal to the order. Okay, and then which here in this case is equal to 1. What am I doing? So the order, what's the winding number? Yeah, exactly. Okay. So here's what is going on. So this thing has to be counted with the appropriate multiplicities. Okay. So if I have a pole of order 2, then it is 2 poles. Okay. In some sense. So then I would write it as, so the question is over how many things do I sum? So if I had a pole of order 2, then I would want to count this, this thing as a sum over 2 things and not just over 1 thing. So really it's equal to, so I can write it in 2 ways. Either I can write it as the sum of this winding number times the order, and then I count only once each pole, no matter its order, or I count its order twice. Okay, so this is clear that it works, but now it's a little bit of a mess. So minus sum of k. So let me just write it. Z equals b of f of c. Okay, if this depends on what is the convention for this order. If it's a pole, should the order be negative? I guess yes. So then we keep a plus in that case. So then it's the order of the poles. Okay, so it's equal to this. But this, so if we regard multiplicities in the appropriate way. Okay, let me write it like that. I hope it's clear what it means. So if we do that, then this is equal to the sum of m of gamma aj minus the sum of n of gamma bk. Okay.
I think we have plus here because the order is k, but the residue is minus k.
So no, but the thing is that what is the definition of order? So you have a pole. Let's say you have a pole of order 2. So is this? I mean, there are kind of 2 viewpoints here. I'm not sure which one is the good convention that we want to use. To be honest.
I think according to what we have written up there, we're supposed to go to minus u because the residue is minus the order.
Well, it depends. I never said what this was. So this could be the order of z equals b of f of z. If I define it like this, then if you have a pole, you can have negative order.
Yes, but we start if this if b is a pole of order k.
Yeah, of order k. Yeah, so then this order function is doing something different. You see, so it counts negatively. I mean, for sure, this is what you say. You never say a pole of order minus k. That is not okay. Okay, so you say a pole of order k, but then the question is, well, is this function supposed to be k or minus k? Okay, and if I say that this function is equal to minus k, then this is correct. If I say that this function is equal to k, then I change to a minus. Okay. Yeah, and this multiplicities thing is, I mean, just to make sure that this is clear. So if I have the function 1 over z squared, and I look at, so it has a pole in z equals 0, but that's multiplicity 2. So what is the order of this function? So it's 2 or minus 2, and then when I write down its zeros, so there are 2 ambiguities. So the order of this, is it equal to 2 or minus 2? Okay? And z equals 0. And the other ambiguity is when I write down the list of these AJs, or BJs rather, BKs. So poles, I can either write it as z equals 0, like, for example, b1 equals 0 and that's it, but with multiplicity 2. Or I can write b1 equals 0, b2 equals 0. because I have two zeros. They just happen to be the same point. And when you write this, you have to think like that. So if you have 1 over z to the n, then the poles are 0, 0, 0, 0, 0, 0, 0, 0, n times. Okay? Not just 0. And in that sense, this formula is true. Otherwise, you need the order. Okay? Confusing? Here. So, forget about this. This is just for the proof. And for this statement, forget about this. We count the zeros and the poles just as simple zeros and poles. Okay? And then that statement is true. I mean, this is how they write it in all the books, by the way. But then you say afterwards, you have to count multiplicities in the correct way for this formula to be true. Okay? So be aware of that, the multiple zeros. Okay. Now, let's give a nice interpretation of this. So now I stated it, I gave a proof, so now you can see where it comes from. Now let's try to give an interpretation of this integral. So 1 over 2 pi I, integral of f prime of z over f of z, along gamma dz. What is this equal to? Well, okay, let's say that we had some gamma parameterized from AB into C, okay? You remember that the curve is its map and is the map and not its image. Now look at this integral. So by definition, it's equal to the integral from A to B of f prime of gamma of t over f of gamma of t times gamma prime of t dt. You remember this? This was the first lecture on integrals. That's the definition of it. But now my function is this, of course. Okay? This is clear. So now we have this. But what is this? Now we recognize the chain rule. Okay. Okay, it's equal to this. And now this is equal to, so if we set now, let now sigma be f of gamma. Okay, so this is another curve, right? So I start with a curve, and then I look at its image for a map. Might not be close though, okay? But it's another curve for sure. That's something. And then sigma prime is equal to f prime of gamma and gamma prime. Okay, you have this thing. This is my notation. Then this is equal to 1 over 2 pi I, integral from A to B of sigma prime of t over sigma of t t. But now, what is this equal to? So if we do this kind of thing, but if we do something backwards, then let's note that this is equal to 1 over 2 pi I, integral not along gamma but along sigma of 1 over w dw. This is the important step, because you see now, to see this we go backwards, right? You have to realize it backwards. If we want to write this on the parametric form, then we put 1 over sigma of t times sigma prime of t dt. This is exactly what we did here. So this is equal to the integral along sigma of 1 over w dw. Okay? And then you see that this is exactly equal to, by definition, of winding number, and you remember that the winding number comes from the logarithm, and that every time the logarithm goes around a lap, then it adds a multiple of 2 pi I. So this is equal to the winding number of sigma around 0. So sigma is this image of this curve. So you look at f of gamma. And then you see how many times it winds around 0. And then you get this integral. So this is a fascinating interpretation, in my opinion. I mean, let's just look at the simplest possible example of this. So, trivial example, because, okay, I don't have a non-trivial example prepared. Okay, so let's do a trivial example. So, let's take f of z equals 1 over z and gamma to be the unit circle. Okay, so you have this, and you have this point inside, and we wonder, so this integral should give the number of zeros minus the number of poles inside of the unit circle of this function. So we know that it has a pole in z equals 0, and that it's a simple pole for your 1. Okay, so now if we look at sigma, which is f of, so this is gamma, so f of gamma. So gamma here is parameterized, so it goes around 1. Right? So sigma equals f of gamma. Then what is this? It's still equal to the unit circle, but it's equal to minus gamma, right? Am I right? It's equal to minus gamma. And then you look at n of minus gamma around 0, because, so n of sigma 0, n of sigma 0 is equal to n of minus gamma 0, which is equal to, you remember this, that if you have a minus sign, you can take it out, which is now equal to minus 1. So this way, you see that this 1 over 2 pi I integral of 1 over z dz around this unit circle is equal to number of zeros, number of poles is equal to minus 1. Is that correct?
We should take the derivative and divide by.
Yes, we should take the derivative. Yeah, okay. You're right, because that was one. Okay, so you know the derivative. Okay, so this is equal to minus 1. So what it means, what I wanted to write was rather, so this has one pole. Well, number of zeros minus number of poles is equal to minus 1. Okay. Counting the order. We can actually not conclude that it was no zeros, but of course we know it. Yeah. Okay, anyway, this is minus 1. Let me take another trivial example. F of z is equal to z squared. And gamma is the same, unit is. Okay? So gamma is the set of e to the I t, where t is in 0 to 2 pi. Okay? Now if I look at sigma is f of gamma, okay, then this is the set of e to the it, where t goes from 0 to 4 pi. So if I am on the unit circle and then I take the function, the square function, then I will go around 2 laps. Okay? If I take z to the cubed, I will go around 3 laps in the same direction. So this means that, and this reflects the fact that you have a double zero, right? So n of sigma 0 is equal to 2, reflecting the fact that we have a double tail, or 2 zeros inside somewhere. Okay, so of course you will not, under any circumstances, use this method to find out that we have one pole of 1 over z, or 2 zeros of z squared, but just to illustrate that it seems to work on simple examples. Next thing you can do if you want a slightly less trivial example is you can take, for example, Möbius transformations. And you can see, do these Möbius transformations have zeros or poles inside the unit disk, for example? And then you look what happens to the unit disk. Is it mapped to another disk under the image of this thing, of this map? And if it's mapped to another disk, does it wind around 0 or not? Okay. And if it's mapped to a straight line, then it does not wind around 0. Okay. So that's my question. So you can try, so exercise, try f of z is a Möbius transformation of your choice. Okay. So let's have a particular good choice. And gamma is unit disk, or a disk of whatever radius you want, and try to find out what is the number of zeros minus the number of poles. Okay. So of course in many cases you will have 1 zero and 1 pole. This is the typical case. But are they both inside the unit disk? Or maybe only one? Or you see? That way. This is a kind of nice natural exercise. And then you can practice again how to do the Möbius transformations. Yes, question?
Yeah, so like this Roman, we don't know if it's true. If we have at the beginning a simple closed curve.
Yes.
Okay, gamma. So what we can say about sigma, the sigma is still closed. We cannot say if it's simple or not. Okay? So we can say that if the number of poles is equal to the number of zeros of f, then the winding number of sigma is 0, is equal to 0.
Yeah.
But this can happen only if f, what exactly does, is take this simple curve and like it double the curve, so like it creates intersections. It's the only possibility where the winding number can turn 0, right?
I'm not sure why that should be the case, or if I'm following.
No, yes. So in general, the sigma is always containing 0 and interior, an interior of the curve.
No.
No. But that's what I don't understand. I mean, it's just.
Yeah, so
like we are saying that if the number of poles is not equal to the number of zeros, then 0 is necessarily an interior of gamma, of sigma.
if it's not equal to, yeah.
So it will
According to
be
this
corollary to this one.
Yeah, absolutely. So yeah, if the number of zeros is not equal to the number of poles, then then sigma has to wind around 0.
Yeah.
Yeah.
But it's not true in general.
No, you can map, if you have the same number of zeros and poles, you can map to something which is just outside.
No, because I wanted to say like, if this is equal to 0, I want to know if it's it can be just because 0 is outside or because there is something that is still inside but there is something happening around.
Indeed. No, but it can be outside. Okay. It can be that just you have a circle around 1.
Yeah.
It can be whatever. Yeah. I mean, simplest example would be z plus 72. You know, you just translate this circle away. Okay.
And in the case if sigma is not closed anymore?
Yes.
No, it cannot be not closed. Because if f is continuous, it cannot break the...
No, it is by definition because gamma 0 equals gamma 1. That's by definition of function, then f of gamma 0 equals f of gamma 1.
Yeah.
So it's closed.
On the other hand, these Möbius transforms, they can send zeros to lines, right? So they can send points to infinity, and they are continuous in a weakly sense. So, okay, this is a point that is a little bit more subtle than that. Okay, let me maybe get back to that after we lecture. Okay. So, now I want to state another nice consequence. You might have heard of something called Rouché's theorem. So the corollary of all of this is the so-called Rouché's theorem. Okay, a lot of French names in this course. Okay, let gamma 0 be closed curve. Such that n of gamma z is equal to 0 or 1 for any z not on gamma. So this is like a remark I said earlier, that if you want to apply this argument principle, it's extra nice to count zeros and poles. It's extra nice if it winds at most ones around any point, right? So it's a simple curve. So assume this. Then we suppose that f and g are analytic. In some omega, and satisfies. So of course omega contains gamma, right? I don't have to write it. And satisfies the following. So to be honest, I find that this condition is always a little bit hard to understand. But it satisfies this condition on gamma. Okay? So not everywhere inside or everywhere, on gamma, on the curve. Okay, so for example, if gamma is a circle, it's kind of typical. Then on the, gamma is, then on actually the boundary of this is on the circle. That's to satisfy this. Then f and g have the same number of zeros inside, so enclosed by gamma. So inside gamma. Enclosed by gamma means inside gamma. Okay, so we have this result. Okay, so this might seem mysterious, I know. This hypothesis seems a little bit random at first when you see it. So now let's see the proof. You can see how you use it, and then we'll give an example, and you see how it works. So first observation is that now it's an English class, neither f nor g has any zeros on gamma, first of all, by this hypothesis, okay? Because you see, if f had some zeros, so if f of z was 0, then you would see that the absolute value of g of z would be strictly less than 0. I mean, some absolute value of something is strictly less than 0. It's not possible. If g has zeros, then absolute value of f is strictly less than absolute value of f. So this is important, this strict inequality, okay? This is based on this screen. So no zeros on gamma. Moreover, this absolute value okay, so if I look at this absolute value, then of course, so what I know, I want to use this hypothesis, right? So then I know that this absolute value is less than 1. Okay? So I will write that soon, but let me just rewrite it in another way. Let me rewrite it as 1 over 1 minus g over f. And this absolute value is less than 1. Okay, now let's call this function defined to be f of z. Okay? So let f of z be g of z over f of z. Okay, it's a meromorphic function. It's like gamma. Maybe f has some zeros. Okay? So apply the argument principle to f and g. And then what we get, so sigma is equal to f of gamma, okay? And what we get is that n of sigma 0 is equal to the integral 1 over 2 pi I. And this is equal to the following sum minus, okay, because in the hypothesis we had this business, right, that it was 0 or 1. So it means that, first of all, the orders are only 0 or 1. So the ones inside gamma. And now, of course, I have assumed that the AJ and BKs are the ones inside. Okay. Here. Which is number. So now it is interesting what this means. Hang on. Gamma. No. It's sigma. Sigma, gamma, sigma, gamma, gamma. No. So this is equal to the number of zeros of f with this, right? Am I being confused? Which one is it?
The point is the number of 0 of f, and the 0 is the number of 0 of g.
Yeah, because f is defined. Yeah, right. So f. Yeah, it's the gamma. It's the gamma. So it's correct. Gamma. But now, what is this? So it is equal to the number of zeros. Because after all, this is the number of zeros not of this little f or g, but it's the number of zeros of f, big F, right? Capital F. So number of zeros of capital F, so number of zeros of g over f. Okay, let's write it like that. So minus, so inside, oh, shit, I feel like I'm messing this up. So let's see, okay, number of poles of g over f. So this is equal to the number of, so of course if you have a 0 of g over f, it means that g has, so actually there are several possibilities. So of course we could have common zeros or poles, right? But if we have common zeros or poles, then we don't care. I mean, in this sum we will just cancel each other out, right? So what we are is a number of zeros of g that are not zeros of f minus, so actually, so I'm not saying that this is equal to this, but I'm saying that this minus this is equal to this minus what I will write now, minus number of zeros of g, of f that are not zeros of g, okay, so it's equal to this. And now let's see how we can finalize this and also check if everything fits together, or if I put the wrong, if I confuse gamma and sigma here somehow, and then we'll just go back and correct that. So then this thing here, this thing, so let's call it star. What does that mean? It means that if I take f of gamma of t, then, so this is sigma of t, okay? So then this is inside the disk of centered at 1 with radius 1, this open disk. So you see that you have this, you have 1, and then you're inside this disk. Okay? So sigma, the idea is this. The picture of the proof is this. But this is sigma. It lies inside this disk. Okay? So in particular, it does not wind around 0. So this thing is equal to 0. Okay? So which means that the number of zeros of G that are not zeros of F are equal to the number of zeros of F that are not zeros of G. Okay, but yeah, and that means that G and F have the same number of zeros. Okay. Zeros inside gamma. Okay, this is supposed to. Then now let's just look again. Did I mess up? Do we need to correct some detailing, or is it correct? Number of zeros. So in this line is the one I was slightly worried about. Right? Is it okay?
But the last line, according to the order of it, if we have a 0 of order n in G, and that point is 0 of order n in P in F, then...
So you have common zeros, you see?
But no, I mean, because we said 0 of G,
Yeah.
such, which is not 0 of F.
Yeah.
But if we have different multiplicity, then it works.
Yeah, so what I'm saying is that, of course, it can happen that you have zeros of f and g at the same time, okay?
But multiplicity different?
But, yeah, multiplicity different. So then, of course, you will get the leftover multiplicities, and the other ones will disappear.
Then it will be 0 of g and 0 of f, but we need to consider that one. I mean, the result is okay, but the last line is like... not clear for me.
Yeah.
I'm not.
But so what I'm saying is that if we have something like something which has Zn over Zm like this, then like let's put some numbers just to make it concrete. Then you can take out two of them because they have the same number. Okay, so we just forget it and we look at 1 over Z3. So we sort of always assume here that we get it. I mean, the common zeros are not seen because we just want to show that we have the same number. So we don't care about the common.
Here, 0 is a 0 of z squared, and also 0 is a 0 of z cubed. But when we count the part, then we need to consider 0.
I mean, so if we look at this function, okay, and this is our f of z, big F of z. Then if you look at, does it have zeros or poles? Well, this has a pole in z equals 0 of order 3. Okay? So we have already cancelled these common zeros when we are doing this business.
No, I'm talking about the last line.
Yeah.
The last time we discussed about f and g, not the big F.
Yeah, so, I mean, this is still correct, right? Zeros of g that are not zeros of f.
Because...
And by that I mean multiplicity. I mean that here we have 0, 0, 0, 0, 0, and for g, and f has 0, 0. Okay? And I say these are zeros for both of them, but these are zeros only for g, but not for f. It has to always be understood in this multiplicity sense. Okay, but these are words to try to explain. I hope. I mean, the important thing is that you understand what I mean by this formula, right? So, okay. but I'm still yes. So yeah, okay. Let's see the applications. I'm happy to explain this again afterwards if you want. Okay. Yeah, so I mean, this would be, I guess, we're warning for all these theorems that the way we are usually phrased, you have to take into account this. I mean, this is a very common idea in mathematics, especially in algebraic geometry, which is the field that deals most with singularities, that multiple zeros count as different points somehow. I mean, you really care about multiplicity. So you have to get used to this. Just because you have the only zero is in some point, if it has large multiplicity, these are to be regarded as different objects. Okay, let's get back to that. Possibly after I'm done. So let's give an example of an application of Rouchet. So let's consider some polynomial here. Let's call it P of Z. No, G of Z. There was a reason for G of Z. Then, let's say that it is Z9 plus 5. So I'm just writing down some polynomial. Now let's see how we can use this. Yeah, unfortunately now I just raised the statement. That was fortunate. So the question is, how many zeros outside the unit disk? This could be a possible question. How many zeros are outside there? Okay, and to do that, of course, we take we consider this disk, and we consider f of z to be 5z cubed. Then, so now you will see this magic. So f of z minus g of z is equal to the absolute value of z9 plus 2z plus 1. Okay, this is less than or equal to absolute value, so just primary inequality. Okay, so of course now we're trying to verify the hypothesis, right? We want to show that this is less than the absolute value of f of z, which was this, on the boundary of this domain, on the boundary of our disk. And what we're trying to do is obviously, so we're asking how many zeros are outside of the unit circle, but of course what we're doing now is showing how many are inside. And since we know how many there are in total, namely 9, because it's a polynomial of degree 9, so if we know there are a certain number inside, we can figure out how many there are outside. Okay, so this thing here, plus 1, so this is less than or equal to, this absolute value is equal to 1. Okay, so 1 plus 2 plus 1, so this is less than or equal to 4, which is strictly less than 5 absolute value of z cubed, which is absolute value of f of z. Okay, I mean this is 5. Okay, so this is on the set when this is equal to 1, because that's where we care. So I said in the hypothesis we have such an inequality on gamma. Gamma is now this curve, the boundary curve. Okay, so by this, so hence f and g have the same number of zeros. Inside of gamma. Okay? So, namely, how many? F obviously has 3 zeros, so namely 3. Again with multiplicity, okay? So it's not just z equals 0, it's not 1, it's 3. Okay, namely 3. And hence this implies that G of Z has 6 zeros outside this disk, or in the attenuated. In this set, Dyrefelt, quite crazy now, this theorem. And so, okay, so in the homework that I will give you today, there is one question to practice this kind of thing. So, of course, I chose to ask for outside, just so you realize that you can sometimes elaborate with these things. Okay, we ask for outside, but let me compute inside, and then I know I can deduce how many there are outside. Or if I ask, so the homework asks about how many there are in an annulus, okay? So how many are there inside such a domain? Okay. Then what do you do?
Repeat this.
Right. So if there are 5 inside this disk and 3 inside this disk, then of course there are 2 in between. Okay. So this is how you do it. Good. Okay. That was what I wanted to say about Boucher. Now there are maybe 10 minutes left. And in these 10 minutes, what do we want to do? I think we want to prove Jordan's lemma, in my opinion. So in these 10 minutes, I will go back to this residue calculus examples. I think this will run a little bit like a red thread throughout the thing. You know, I will sometimes talk about something, and then second half or end of the lecture, depending on how much time I have, I will go for more of these residues that I have prepared several examples. Okay. So let's prove Jordan's lemma. So Jordan's lemma. So you recall that we wanted to apply it to something like, what did we want? We wanted to estimate, so integrate this kind of thing on a big circle, okay? Or a small circle. This is what we wanted, no, actually on a semicircle. This is what we wanted to estimate. And the lemma is exactly about such things. It's about when you have e to the I t or I 2t or half t or something. That's a positive multiple of this, and then some other function. So let me recall the statement. It was like this. Okay, so this thing is simply this curve, right? So on this upper half circle. So you look at the maximum of the absolute value of g. Then this integral, so the absolute value of this integral. So let's call this CR, okay? So then the absolute value of the integral on CR of g of z times e to the I alpha z dz is less than or equal to pi mr over alpha. This was the lemma. And then if you apply it to this theorem, okay, let's just see how you would apply it. Then you would take g of z is equal to 1 over z squared plus 1, and alpha is equal to 1. Okay? Just to understand what we're doing. And then we would get that the absolute value of this integral, okay, e to the I, it's not, this is a z, right? E to the I z, z squared plus 1, z is less than or equal to pi or alpha, so pi divided by 1, okay, let me write it, times mr, which is the maximum of g of z on the circle, on this upper circle, okay, which is equal to pi times 1 over r squared minus 1. This is the biggest you can get out of this when absolute value is equal to r on this upper circle. Okay? And now the point is that this, then r of course is supposed to inversely different, we want r to become big. So this will go to 0 as r goes to plus infinity. I don't know if you remember exactly where we ended last time, but this was what we had left to do. Apply the lemma. Okay, well now let's give a proof. So why is this true? Okay, so so we try to first look at this. So f of z is of this function. Okay, so let's say this is f of z. Okay, so this is equal to then the integral from 0 to pi. Let's just parameterize it along this semicircle, okay? From 0 to pi of g of, so the absolute value is r, so g theta, times e to the I alpha r cosine theta plus I sine theta, let me write it like this, times I r e to the I theta d theta. Due to lack of space, I wrote it like this. Otherwise, it's not so customary to write down. That's equal to this. And this here is equal to f prime of this CR of t. And this is CR prime of t. Of theta. Okay? So, what we get, this is d theta. So this is what we have. So now using this fact that sort of triangle inequality holds for integrals, that the absolute value of integral is less than the integral of the absolute value. So now we get that this integral that we're interested in, so this is, let's call it IR. So this IR, its absolute value is equal to, so the absolute value of this is u to z. This is less than or equal to, now we have an r here, r times integral from 0 to pi of absolute value of all this business. And then the absolute value of this, e to the I alpha r cosine theta plus I sine theta. What is this?
Minus alpha r sin theta.
Minus alpha r sine theta. Very good. Very good. D theta. Okay. So it's less than or equal to this. This is clear because, of course, also this has absolute value r. This is what I took outside. Now, this is less than or equal to, by a trivial estimate, now I don't want to carry around this. So this is equal to r, the maximum of g of c, where z is on this CR, okay, times whatever is left, integral 0 pi of e to the minus alpha r sine theta theta, okay. And now let me erase here. Okay, so, and this was MR, of course. So now we care about this, this integral. So what can we do with this integral here? E to the minus alpha r sine theta. Okay, so we look at sine. Okay, this is the sine function. This is equal to pi halves. Okay, this is the theta axis. Okay, this is sine theta. And this is y equals sine theta. And then you can look at this straight line here. This is a terrible picture, but look at this straight line. Okay, do it in another color, please. Okay, what is this straight line? This is supposed to be y equal to 2 over pi, right? So we have to do it the other way. Y equal to 2 over pi times theta. Okay, it's clear of a picture I drew, right? And now we get from this that so for 0 for theta between these things, we have that sine theta is greater than or equal to 2 pi 2 over pi theta. Okay. This is by concavity, simply of a function on this approach of the real axis. So now, if we continue from down here, so this is less than or equal to r mr, and then integral from 0 to pi, go to pi halves. Yeah, I lost. Exactly, yeah. Okay, so let me say that this is equal to two times this thing from 0 to pi half. Okay, okay, and now this is why I consider this. Sorry. Yeah, that's what that was the entire point. Thank you. So 2r and r, and now the integral of 0 from pi over 2. So we use this fact, but on this interval we now know this. So e to the minus alpha r 2 over pi theta. Okay. So of course sine theta was greater than this, but you get less than or equal to here because it's minus theta. And now this thing here you can actually compute it. So this is equal to 2r mr times minus pi over 2 alpha r. Where is this? E to the minus 2r alpha theta over pi. If you have this, and you cancel these things, this thing cancels, okay, and you get that this, and you evaluate this, sorry, that's 0 I have, and you will see that this is equal to pi over alpha times 1 minus e to the minus alpha r and r. Okay, and since this thing here is greater than 0, then we see that this is less than or equal to pi over alpha mr. So actually this would be a more precise bound, but somehow we just ignore this because we'll complicate things and get something less strong. This would be it. So then so this way we prove this Jordan's alpha. And I mean, this is something essentially always you apply this. So when you have a residue theorem, you always get a part that you want to show goes to 0 or something essentially, when r goes to infinity. And then one common tool is Jordan's lemma. when you have this semicircle or semicircular domain. Okay, but now time is my